Now, today we start the chapter 1, that is the real number. Now, real number we have discussed in class 9 or earlier classes also. In that class, we learned the set of real numbers is a combination of rational and irrational numbers. Now, here in this real number, we understand some basic concept of these numbers also. In this chapter, we discuss 2 or 3 main parts. One is Euclid division lemma, another is fundamental theorem of arithmetic, and then third is the proof of irrational numbers. So first, we discuss the Euclid division lemma. The word division you already learned in earlier classes. We divide a number by another number. But the same statement or the procedure or the relation between the numbers is known as Euclid division lemma. So Euclid division lemma is for two positive integers, for two positive integers a and b, where a is greater than b, there is a unique integers q and r such that a is b into q plus r, where r is less than b and greater than or equal to 0. What is that? Basically, a and b are the two numbers, as we have done in earlier classes. When a is greater than b, so when a is divided by b, so b is the divisor. And after division, we get a quotient and a remainder. Sometimes, now the remainder is either it is 0 or less than b. So this is nothing but dividend equals to divisor into quotient plus remainder. So the value of r lies between 0 and b, but r is never b equal to b. It is less than that, means it is less than the divisor. Remainder is always less than the divisor, or it is equals to 0. For example, if there are two numbers, if 25 and 7 are the two numbers, how we write these numbers? By Euclid division lemma. 25 can be written as, means 25 is divided by 7, so it is 25 is divided by 7 into 3 times, 7 3s are 21 and 4 is the remainder. So 3 and 4 are the unique number, means 25 and 7 can be written as in this form. In other words, we can say any number or any integer, positive integer, can be written in the form of bq plus r, just like this. So this is the representation of 25 and 7 by using Euclid division lemma. Now here, what is the use of these division lemma? Here we find the HCF of two numbers by using Euclid division lemma, as in exercise 1.1. There are several questions in which we have to find the HCF by using Euclid division lemma. Now we take an question number, some questions of the exercise. Now so take an example, that is the question number first of exercise 1.1. Here find the HCF of two numbers 135 and 225. Find HCF of 135 and 225 by using Euclid division lemma. This is our question number 1 of this exercise. So here you can see 135 and 225, there are two positive integers. Clearly 225 is greater than 135. So we can write by using solution by using Euclid division lemma. In short form we can write EDL. 225 can be written as 135 into 1 plus what will be the remainder? That will be 90. If we divide 225 by 135, the quotient is 1 and remainder is 9. Again 135 can be written as, again the next step, 135 is divided by 90, so 90 into 1 plus 45. Now next, in the third step, 90 can be written as 45 into 2 plus 0. In this step, what we get? In the last term, that is, we recall it, remainder becomes 0. So when the remainder becomes 0, since remainder r is 0, so therefore the last divisor, that is 45. So 45 is the HCF of 135 and 225. So this process, by using this statement Euclid division lemma, we follow the same relation in different steps. This is known as, this set of process is known as algorithm. Sometimes this process is called Euclid division algorithm. The algorithm word is new for you. Algorithm is what? It is a definite and defined steps to solve a particular problem. So that is called the algorithm. And what is lemma? This is also a new word. Euclid, the name of person. Division is a mathematical operation. But the word lemma is a proven statement. Lemma is a proven statement which is used to solve some other problems. So that is the word lemma. I think you understand what is Euclid division lemma. How we find the HCF of two numbers? By using Euclid division lemma. That is the algorithm. By using this lemma, this statement in certain steps. Now, in sometimes you will feel difficulty to write this. There is the other way you can write this process, which you have done in very earlier classes, 4th, 5th classes. Now you can write it 225 is divided by 135. So it will divide it 1 times. So 135. When we subtract it, it becomes, remainder is 90. So this remainder becomes the divisor and 135 is the dividend. Again it is 1 times. So we have 45. 45 is the divisor and 90 is the dividend. So it is 2 times. So 90, we get remainder is 0. So this is nothing but a process of division. So I think everyone understand what is that. We write this process according to the Euclid division lemma. I think all of you understand what is that. Sometimes you can get remainder 0 in very first step. So you need not to solve other. You get the last divisor is the HCF. Okay. So I think for your convenience we can write one more example. That is the second question. Find the HCF of 196 and 38,220. That is the second question. Find the HCF of 196 and 38,220. So here we adopt the same process. I think this is a very simple question which we have again you find these two numbers, which one is greater? Clearly 38,220 is the greater number. So what will be the divisor? 196 will be the divisor. But you cannot write how many times it will divide orally. So you can do the division in side way. You can find 196. Clearly it is 1 times, which is 196. So after subtracting we get 2, 6, then 8, 186, again 2. Now 196 is the divisor and 1862 is the dividend. So again we divide, it will be how many times? 9 times. So 4. That is, now you subtract, it is 8, then it becomes 9, 0, 0, then 980. So I think 5 times, 5 6 are 30, 3, 45 plus 3, 48, 4, 5 ones are 5 plus 4, 9. So again we get remainder 0. So you can write 196 into 195, and what will be the remainder? It is 0. So in this question we get in first step, very first step we get the remainder is 0. So what we, since the remainder is 0, so we need not to write one other steps because we get remainder 0. So since remainder is 0, so therefore the last divisor, that is 196, is the HCF of 196 and 38,220. So I think all of you understand what is the procedure to find the HCF of two given numbers. So that is, there are so many questions, other questions given in your textbook. You can simplify the way of writing. I think you understand very much. Now here we take the question number 4 of the exercise 1.1. This is another use of Euclid division lemma. In previous part we have discussed how we find the HCF by using Euclid division lemma. Now here the question is, use Euclid division lemma to show that the square of any positive integer is either of form 3m or 3m plus 1 for some integer m. Now means we can write the square of any positive integer. So first we have to assume let a be a positive be a positive integer. So by using Euclid division lemma, A can be written as 3b plus r. A can be written as 3b plus r, where r is less than 3 and greater than or equal to 0. So when we put, or you can write r is 0, 1 and 2. You can also write this. The value of r is lying between 0 and 3, means 1, 2 and 3. So for r equals to 1, for r equals to 0, first we take r is 0, then a becomes 3b. This is the integer, positive integer. Now the square of a is, if we do the square of the right hand side, it becomes 9b square. So this can be written as 3 into 3b square. Now if we write 3b square is m, so it becomes 3m, for m equals to 3b square. What we have done? We replace 3b square by another integer, that is m. So a square becomes 3m. This is number 1. Means a square of this a is in the form of 3m, which is this one. Again, for r equals to 1, a becomes 3b plus 1. Now again squaring, a square becomes 3b plus 1 whole square. By expanding this, it becomes 9b square plus 6b plus 1. Expanding by using identity a plus b whole square, a square plus 2ab plus b square. Now from here, from these two terms, we take 3 is common. So we have 3b square plus 2b plus 1. Again, we replace this by m, so it becomes 3m plus 1. This is number 2. This will be an integer, so we replace by m, some integer. Don't be confused that here m is 3b square and here m is 3b square plus 2b. This is just a representing this number by an integer. So this will be an integer, again here this will be an integer, so we replace by m. So again, for r equals to 1, the square of a positive integer is in the form of 3m plus 1. Now for r equals to 2, a becomes 3b plus 2. Again squaring this, a square becomes 3b plus 2 whole square. Now again by using identity a plus b whole square, it becomes 9b square plus 12b plus 4. Now, is that can be written in this form or not? Look at here, if we write this expression in this form, 9b square plus 12b plus 3 plus 1. We can split 4, we can write 4 into the form of 3 plus 1, that is 4, and the remaining terms are the same. Now here we take 3 is common. So taking 3 is common, it becomes 3b square plus 4b plus 1. Again plus 1. So by this number, this is an integer, so it is 3m plus 1. This is number 3. Now from this relation 1, 2 and 3, we find that the square of any integer which is in this form, 3b plus r, its square will be in the form of either 3m or 3m plus 1. Hence, it is proved that the square of a positive integer is either in the form of 3m or 3m plus 1. So from 1 and 2, from 1, 2 and 3, it is proved. So this is the exercise 1.1. There are different questions in the exercise. Basically there are two types. One is find the HCF, another is by using Euclid division lemma, we have to write a number or an integer or its square or its cube in a such form. So I think you all understand this. Now in the next part we will discuss the next, that is the fundamental theorem of arithmetic, as well as the relation between the HCF and LCM, which is of the exercise 1.2. Okay, thank you.